Record, share screen. So the mission now for the next at least couple of days is to find zeros of unfactorable polynomials. This is a big deal. So what happens is, well, yeah, so today is 11 or 10/18, and we are finding rational zeros of unfactorable polynomials. And by the way, when I was typing up your worksheet earlier, unfactorable got flagged as not a word. I cry foul. I believe that it should be a word. So I added it to my computer's dictionary because I think it should be a word. Unfactorable. If you're not factorable, you're unfactorable, right? Just put that anywhere, Christian. Just, you got her? So what we've practiced to this point, that last quiz that you guys took was, if I give you a polynomial that's factorable, you identify a strategy. Like you pull out a GCF and then do grouping, or you pull out a GCF and then you treat it as like, oh, it's a lookalike, and then it's a difference of squares, stuff like that. What we're going to see today is on the first level of this, you're not going to be able to factor. And there might be occasional examples where you look at it and go, well, I can factor this. But by and large, what you're going to find is when we look at the problem originally, you're going to go, I don't know what to do with this. And this is where something comes into play. So let me show you an example of what I mean, and then we'll talk about what we're actually doing here today. So I had this marked as example number 1. So here we go. I number these to make sure I don't give them to you in a unsensible, senseless order. We've been through enough of this together that if I gave you this problem, you've learned well. You've got just almost to a person. We look at this and we do exactly what I want us to do. Number 1, we look for a GCF. There isn't one. Number 2, we default and say this must be a grouping problem. So we would instinctively draw the wall down the middle, and then we would quickly run into a wall. Like, not, no pun intended there. Like, so if I tried to wall this and I attempted grouping, I would say, okay, what's the greatest common factor on the left? X squared, and that leaves behind x minus 3. Because this is kind of what I've taught you to this point, is this hopefully would work, right? And then right, it won't work. And then when I bring down the minus, no matter how hard I try, I can't get things to match the way I want them to. So like if I can manipulate that second half all I want, I'm not going to get this to work. I hope you see what I mean by that. And so when grouping fails, and when it's not a factorable quadratic, or when we hit the wall, then we rely on much, much, much more useful and heavy ammunition. And that's what today is all about, is something called the rational root theorem. And you're going to notice, by the way, that I keep throughout the day, eventually you might want to ask, what is this? Why do you keep saying rational? And when we talk about rational roots or zeros, by the way, start using the words roots and zeros sort of interchangeably, okay? We generally think of a root as more the solution of an equation. And then when we change it to the word zero, we more think of it in the context of the physical place where the graph crosses the x-axis. But just so you know, they're kind of the same thing. So the rational root theorem is also by some people called the rational zero theorem. And when we talk about the word rational, what that means is things that can be expressed as fractions or like whole numbers. So rational roots are things like x equals 2, x equals -1/2, x equals -3/4. These are all what we call rational numbers. There are also, of course, a lot of irrational roots, things like this. So this, we will not go down this road today, probably even tomorrow. But there are lots of quadratics and cubics and fourth degrees that have irrational zeros. Things like, my graph might cross the x-axis at -2 plus the square root of 5/3. That yellow thing is an irrational zero or an irrational root. Or through the course of like the quadratic formula, we might find that one of our zeros is at x equals the square root of 4 or the square root of 2, something like that. That's an irrational zero. So for the purpose of today and tomorrow, we're going to talk only about rational ones like 3, 2/3, -4/3, 5/2, 1, 0, stuff like that. Okay, the numbers that we like the numbers we can kind of get our head around. But as that word keeps popping up, and it will a lot, the word rational, just be advised, that refers to things, basically, in a nutshell, things that don't have roots in them, square roots, right? So if it's a nice normal number, fraction, whole number, whatever, then it's called rational. And so that's why that word's going to just keep showing up and keep showing up. So what we're on the search for today is answers like the purple things. We're looking for rational zeros, rational roots. In the rational root theorem, here it is. He's back. The fly's still here. There's another one. I don't want to record myself acting like a psychopath, so I'm either going to have to ignore the fly or pause the recording. Just pause it and go ham on the fly. Yeah, just give me a second. All right, so here it is. And this won't be the last time it comes up because you're going to be like, what? I go into this and I want to know, for that white polynomial, I want to know what might be some answers to this problem. And everything I'm going to give you today and tomorrow has only rational roots or rational zeros. So the question is, what are they? And I mean, one alternative, and I want you to know that I'm aware of this, just full disclosure, what's to stop me from just typing it into Desmos, looking at the graph and saying, there's my zeros, boom, boom, and boom. So if that thought occurs to you, know that it's occurred to me too, okay? But I can't not teach you this. So for the next couple of days, we're not going to utilize technology. Like on the ACT, they're not going to certainly let you bust out Desmos, right? So we need to be able to manually look at a graph or a function like this and say, where could this graph mathematically maybe cross the x-axis? That's the mission. And that's what the rational root theorem gives us. So here's how it works. You take the number in back, which is 12. And I want you to notice that I didn't say -12 because I'm not interested in that. And I'm going to write that down on the top of a fraction. This will get harder and harder, by the way, as we go. And by harder, I just mean there's more meat on the bone. Like there's more candidates, and you'll know what that means in about 1 minute. And then I'm going to take the number in the front of the problem, which is 1, and I'm going to put it on the bottom of the same fraction. So my fraction currently consists of 12 and 1. Now, the fact of the matter is the rational root theorem is pretty rad. What it states is that if this function has rational roots, they exist in the form of a factor of the yellow number divided by a factor of the purple number. Fractions. And these are nice, and I'm going to let you have your first couple, 3 examples. I'm going to be really nice about this, and I'm going to keep the purple number at 1. And that's a big deal because when I make fractions with a bottom of 1, they're not really fractions. So the positives and negative versions also have to be taken into consideration. So first, let's make a list of all the factors of 12. What are they? 1, I would be organized if I were you. 1, then 2, then, good. And what are all the factors of 1? Good. So what the rational root theorem says is I have to take those now and build every possible fraction out of the yellow numbers and the purple numbers. And I have to consider the positives and negatives of them both. So, for example, and again, I would encourage you to be organized, and you'll know what I mean when we get to like the 4th example today. You'll go, oh yeah, this can get out of hand in a hurry. So I'm going to take the first number, the first yellow number 1, and I'm going to say that one possible rational root of this function is either positive or negative 1/1. That's me taking this first yellow number and dividing it by this purple number and making a fraction. And I'm not some crazy crackhead. I'm not going to write it as 1/1 because that's going to make me think that it's like something it's not, right? Now I'm going to work my way down from or across from left to right, and I'm going to hit the second yellow number. What's my second set of possible rational zeros? Positive and negative 2 over 1. Keep going. What's next? Good. Next. 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 And listen, this is what I'm about to say. You're going to think, my God, that's a lot. There's going to be a lot more as these get harder. Right now, there are 12 possible candidates for places where this graph could cross or touch the x-axis. 12 of them. 1, 2, 3, 4, 6, 12, and then the negative versions of all of those as well. Which leads me then to this question, well, how am I supposed to know? That's why we practice synthetic division for 2 days, is so that we wouldn't be burdened with having the process of checking these take longer than it needs to. If you're not quick at synthetic division yet, you should get there. But again, those little mistakes, they're not, let's stop laughing about them and making it light like this is, because now we're going to be crippled if we do stupid little things like say, 3 minus 6 is 3, 11 minus 15 is 4, 3 times 4 is 7. Those are going to crush us because as we go through this list of 12 numbers now and we check them, what a shame it would be to have tried the right answer and missed it because of something dunce cappy, some little rinky dink arithmetic error. So we're going to have to hold ourselves to that super high standard as we go through this next step and say, I'm not going to make little mistakes. I mean, who am I to say that? Like, we're human, but I'm going to really, really try not to. That's the goal. So what we're going to do now is we're going to take the original polynomial up there at the top, and we're going to synthetically mess around with it using the numbers that I've written in white down at the bottom of the TD. So let's begin. And for this part of it, it's not a bad idea to sometimes use pen because you're going to be doing a lot of erasing, just FYI, but you don't have to. So I'm going to take the numbers from my polynomial and I'm going to put red around them for you just so you remember from yesterday. 1, -3, -16, bless you, and -12. And I'm going to set myself up now for some synthetic substitution or synthetic division. So 1, -3, -16, -12. And I'm going to scroll way up now so that I only see on my screen the list of possible candidates. And I still have something blocking, so I'm going to move just a little bit here. There we go. Good. Got it? All right, so we're going to set up our upside down division symbol thing, house, whatever you call that thing. And we're going to start testing. And this part, some of you won't like very much, but I don't know what to tell you other than just it is what it is. So this is where we play a guessing game now. And what you have to do now is pick a number off of that list and say, I'm going to try you. I'm going to try to synthetically substitute you and see what I can get. So what do you want to try first? 4. 4. Totally random, but I love it. So let's try 4. So what that means for me is I'm going to stick 4 out here. And if this takes you a minute to do each of these, you're in for a really long couple of days. This needs to be lickety split. And as I was watching some of you yesterday, you get through it pretty quick. Drop, times, add, times, add. This should take 10 seconds. That's where you should be, if that. So let's test this. And what are we going for? Like, what are we hoping to see? No remainder would mean that 4 is a 0. And that's significant because I'll show you when we get there. And I know what the answer is, but I'm not going to guide you in any way. We're going to go through this together. So let's test 4. So we drop the 1, multiply 4, add 1, multiply 4, -12, multiply -48. And of course, we got a remainder of -60. So we can now take 4 off our list. Thank you, Evie. We agree 4 does not work. What else would you like to try? 3, did I hear? Great. And so plan to erase a lot. And that's why I say doing part of this in pen is a good idea because then you won't be erasing over the part that is like this part that I've got up on the screen is like permanent. This is my permanent ink. I'm going to be erasing the work around it. And you said to try 3. So let's try 3. And again, just knock it out quick. 1, 3. Ooh, that's ugly. 0, 0, -16. You stop right here, right? Do you need to go further? God, no. -48, again, is not going to work. So 2 down, 10 to go. Maybe 2 down, 1 to go. Because once we find 1, I'll show you The others are easy to find. On today's and tomorrow's version of what we're doing, they're easy to find. What else would you like to try? -2. I like it. Again, somewhat random, but I like it. And by the way, you should keep track of what you've tried. So, I'm not doing that up here. I kind of figured you guys would go in order, but whatever. So let's check it. Drop the 1, multiply -2, -5, multiply 10, -6. And we have, I figured when you said that you knew something that we didn't know. And we got it. Good job. This is a really big deal. That's a great moment. And you're really going to come to appreciate the warm, fuzzy feeling that comes with what just happened. That means that the problem now is essentially over. It means that we have found one of our zeros. We can now say that this graph either touches, snakes through, or old school crosses on the x-axis at -2. That's a big deal. Now, what we're going to do is we're going to take the remaining 3 numbers and we're going to build a polynomial out of them. Everything I'm giving you today is a 3rd degree function. So once I can peel one layer off of the onion, once I can find that one, and you got us there, once I can find the first one, what do these 3 numbers stand for? And now, if I want to find the other zeros, listen, if you're some kind of masochist, you could keep building synthetic division symbols down off of the 1, -5, -6, and keep testing zeros. But why do that when I've got myself down to a familiar place called Quadraticville? Can we factor the white polynomial? Yeah. All day. That should be light work for us, right? So by peeling off that top layer, we've exposed a polynomial that's going to then feed us the others without having to do all that synthetic rigmarole. So this factors down, of course, into x minus 6 times x plus 1, and the e reveals the other 3 zeros, or the other 2 zeros, excuse me. So if we make a list of answers for this problem, we can now say, here they are. This graph crosses, and I can say crosses now because they're not multiplicity, so there's no weird behavior. This graph crosses the x-axis at -2, it crosses the x-axis at -1, and it crosses the x-axis at +6. That's powerful stuff. Because if all we know is how to factor, then we're going to hit a wall and go, well, if I can't factor it, I guess it's just a dead polynomial, and that's not true. Just because you can't factor it doesn't mean that it wasn't built from factors. Does that make any sense? Yes, ma'am. Because I wanted to make this red box down here equal 0. So remember that? Yeah. Okay. 1 down, 5 to go. Yeah, that's what we're going to go for today. Is today's questions, when you get to the assignment, are going to ask you to do 2 things. Number 1, state all possible rational zeros. So good question, Bryce. The first answer, if you will, like when we take a quiz on this will be, what I'm putting in a red box is an answer on a quiz. This is a list, Mr. Ahern, of all the possible rational roots that I need to think about. And then the second answer is to find all the rational zeros, and that's the second red box. Good question, Bryce. Good. All right, let's do another one. So our second function is f of x equals x to the 3rd minus 5x squared minus 2x plus 24. According to the rational root theorem, all possible rational roots are going to be found and exist as fractions built from the number 24 and the number 1. And again, I'm going to keep our first 3 examples with 1 on the bottom so that we don't have to worry about anything fractioning. So the list of factors for this, the list of possible rational zeros is at positive -1, positive -2, positive -3, positive -4, positive -6, positive -8, positive -12, and So we have a longer list this time. So we as a class might want to divide and conquer. And you'll find this, like I know that like with Sutter and Christian working together, and a lot of you work in pairs, like maybe like Austin and Tyson are going to work together. I don't know, but it's a good idea to divide the task. I'm okay with it in this case because like Sutter's like, you know what, I'm going to try 1 through 4, and Christian's like, I'll try 6 through 24. And then if you pair off like that as a team, you can get to you can't do that on a quiz, but on homework, you can get to your destination quicker. If you're in a group of 3, then you're really going to go quicker, right? Ready? All right. So we're going to put our numbers across the top and prep for synthetic divisions. We're going to have a 1, a -5, a -2, and a 24. We're going to draw our upside down division sign. And remember, if this part you do it in ink, make sure you don't mess up. And then the number that you put out here, don't put it in ink because you're going to be erasing him a lot. Now, you don't want to rewrite this whole thing. So just what you do is you put that in ink and then the rest is pencil because we change a lot. So sure, yeah, that would be something you could put in ink. So like right here, you could put a 1 and just say that's always going to be there. Sure. Yeah. I'm just trying to think as a guy who's done this a lot of times, like what can I do to make your lives a little bit less, repetitive. So let's throw it out. Sutter guessed well last time. You want to guess again? Sutter might be our lucky. Did you test it and does it work? Yeah. you guys get so lucky. That's amazing. So if you try 4, let's see if it works. Sutter feels pretty good about this. Drop the 1. 4 times 1 is 4. -1 multiply -4, -6, and sure as all get out, we got ourselves another 0. So Sutter is our he's laying golden eggs back there for us. And again, what's nice is I have found one of my answers now. I can now say I am sure that the graph interacts with the x-axis in some way at the number x equals 4. 1 down. And where am I going to get my other 2? By factoring. And the factoring that I'm talking about comes from these 3 numbers that I'm underlining. Remember, like we learned yesterday, synthetic, you peel that first layer off, you drop the degree, so it comes down to x squared minus 1x minus 6. And of course, how do we factor that down? That's it. And I wrote, when I did today's assignment, I threw no curveballs at you. They're going to get harder, you'll see here in about 5 minutes, but there's no curveballs in that you can't find what I want you to find. If you're following this method, you're going to find them all. They'll pop out. So my other answers, I got x equals 4. What's another one? And x equals -2. Good. So remember, each of these things down here in this gold box at the bottom, those are answer producing factors. Did you say 6? Yeah. You okay? I don't know. Do you have this in your notes? I'm pointing to it with yellow arrows. Okay. Do you want to talk about why you said 6? I'm not trying to pick on you. I just want to know. You sure? Okay. Good. All right, I got one more, I think, warm-up easy one for you. So this one should go. Watch out, though. There's a little trick, a little curveball here. So the function, we'll just name him g of x because we always do f of x. And g's like, what about me? So let's call him g of x. Is x to the 3rd minus 7x plus 6. So step 1, let's make a list of all possible rational zeros. And they are what? Positive, negative, positive, negative. Those are them. And remember, if you're sitting there going, gosh, I wish someone would ask how he's getting those, here, I'll say it for you. Remember, I'm taking factors of the number in back, the constant term. The number in back is the constant. And I put all of his factors, 1, 2, 3, 6. And then I take the number in front, which is the number 1, and I list all of his factors. And remember, the only factors of 1 are 1. So that's why none of my answers for now are being expressed as fractions, because I don't need them. So again, let's prep it. What numbers am I going to lay out for synthetic division?
0.
Yeah, so that problem really attracted me to the notes this morning because I wanted to make sure you're aware that that can still happen, guys. You know, if there's a missing term, you still have to fill that hole with a 0. So, and then like Tristan said, if you want to, for permanence sake, you can drop the 1 and let's begin. Is our golden egg going to happen again back there? You got a 1 in 8 shot if you just pick one. If Mason's like, I don't know, -6. That's a 1 in 8 shot. All right. First try again. What is with you? What'd you get? Unbelievable. And what did you try? And did it work? Okay. So this is an interesting sort of phenomenon. And I actually want to take this chance to teach you something. Not all of you will go, ooh, that's neat. But some of you will go, ooh, that's neat. So let's do Sutter's first. If I do Sutter's 2, kid seems pretty confident that this is going to work. So I'm going to go 2 times 1 is 2, add them up, 2, 2 and 2 make 4, add those up, -3, ensure enough. So if I do Sutter's approach, at the end, I'm going to be factoring the polynomial x squared plus 2x minus 3. Rad, right? I could do that. I could do that in my sleep. But I want to show you something. Let's use Christian's. So on Christian's problem, I'm going to set it up the same way. 1, 0, -7, 6. And then I'm going to upside down divide. And you said -3, Christian? So let's take a look at, I think this is interesting. And again, a few of you might go, whoa, neat. So it's, you know, there's not one way to do this at the beginning. This will prove that point. If I do Christian's, bring down the 1, multiply -3, add -3, multiply 9, add 2, multiply -6. And it's like, well, that's cool. So here's what I think is neat. If I do it Sutter's way, the first answer that I found is x equals 2, right? And then I factor down his polynomial into x plus 3 times x minus 1. And I find from there the other two answers, x equals Christian's and x equals 1. Rad. But if I do the Christian method where I find the -3, which one I stumble upon first is, I'm just happy I found one. It doesn't matter which one it is. But if I do Christian's method, the remaining 3 numbers spell out x to the second minus 3x plus 2. And when I factor Christian's expression, I get x minus 1, x minus 2. It's neat. Like everyone is still accounted for. On Christian's side of things, the one we found, or he found, excuse me, was x equals -3. But the ones that we find from his factoring are x equals 1 and x equals 2. And when you look at either side of the problem, you still can check them off. Look, 1, 2, -3, 1, 2, -3. You should find that remotely interesting in that. So which one I find first is still going to lead me to a place that will then expose the others. Doesn't matter what the first one is. Got it? Brycey, you doing okay there? All right. Any questions so far? All right, on to example 4. Let's call this one h of x. And his meat and potatoes, his business end is 2x to the third plus 7x squared minus 17x minus 10. It just got a little bit different in here because of what I did. I put a number in front of x to the third. So that means that the rational root theorem just got buffed. It just got like doubled in workload. So let's go back and focus on what we know. Remember, we're going to take all the factors of the yellow number 10, and their names are 1, 2, 5, and 10. And then on the bottom, we're going to take all the factors of the purple number 2. And what are they? 1 and 2. And you see now that fractions are officially in play. So as I go through and I build my list of all possible rational roots, I have to be cognizant of the fact now that because of the 2 on bottom, some of my answers are going to be fractions. This is where it becomes imperative that you not be some random, like, you know, sugar hyped up monkey who's just grabbing things. We want to be methodical. So what I like to do is take the first number in the top and write both versions of him. So one of my possible rational zeros is positive -1, and the other ones are positive and -1/2. So that, remember, is built from the top number and every possible denominator from the bottom. The first one's not a fraction because who needs fractions when the bottom's 1, right? So let's head on to the second number. And for this one, I'm going to color code it in red. So now if I take the 2 and I build all possible rational zeros out of him, what's the first one? Positive -2/1. And what would the second one be? Good. And you're going to find yourself doing this a lot. And Bryce was about to say this before I interrupted him. This is redundant and you don't need to list it again. You'll find yourself sometimes writing it and then erasing it. But what is 2/2? And we've already got that one right here. So you don't need to list that one again. I hope that makes sense. Now let's head on, and I'm going to recolor code this in green. So now let's take the green number and build all possible rational zeros out of him and the guys below him. What's the first one? Positive and -5/1, which is 5. And what's the other one? Good. And neither of those is redundant, so they both have to stay. And I'm about out of colors here, but I guess I'll just use yellow because I haven't really, it looks a little weird, but let's do yellow. And so the 10 now is up to bat. What are his possible combos? Positive and -10/1, which is just 10. And what's the other one? Positive and -10/2, which is positive and -5, which is already on the list, so I'm done. Don't write down redundancies unless you really want to for some weird reason. So my advice to you, because now it begins to get a little nasty, but to keep it friendly and real and easy for today and tomorrow, my advice to you is you should try the whole numbers first. Because I haven't done synthetic division with fractions with you yet, so I'm not going to expect you to do it yet. So let's stick to the wholes and hope that we can pop a nice whole number out so that the fractions come out in the factoring. Because there are going to be fraction answers, but I don't want you to try to find them first. So basically what I'm saying to you in my long-winded way is let's try 1s, 2s, 5s, and 10s and hope we can expose the others some other way. Well, golden egg boys back there, what do you want to try? 2? You already tried 2? Sir Speedy? So let's set it up for synthetic. We got 2, 7, -17, -10, upside down division thingy. We really need to come up with a name for that. And then you said 2 works? Yeah. Dope. Let's try 2. Remember, there are 12 possible rational roots. 1, -1, 1/2, -1/2, 2, negative, so on and so forth. So if this one works, great. That's a 1 in 12 shot. Now, it's a little better than that. No, it's not. Anyways, let's do this and let's see if it works. So drop the 2. Not that I don't trust you, Bryce. I'm sure it works. So drop the 2, 4, add 11, 22, add 5, 2, 5, 10, add 0. Perfect. Jackpot. So that means that we have found a rational zero. We now know that the graph interacts with the x-axis at x = 2. Does it bounce? Does it snake? Does it cut? I don't know. It depends on whether I find any more of that root or not. So now I'm going to use the 3 red numbers at the bottom, and I'm going to build a polynomial out of them. And I'm going to hope that I'm not one of those people that just sits back and says, oh, I suck at factoring, because that's not okay. Can I factor this? Everything okay back there? Okay. So I'm going to put a 2x and I'm going to put a 1x. And I know that they're all plus signs, right? And if there's not a lot of options here. So obviously you want to put the 5 polar dead across from the 2 to make the 10 and then put the 1 here. So what were the other rational zeros now that pop out? -1/2 and there they are. By now you should fully understand what we're doing today, right? Listing the zeros, testing until you find one, and then use the one, peel that first layer off, factor down the rest. Let's go again. Let's call this function j of x. 4x³ plus 17x² minus 39x plus 18. So remember, the idea is that our answers, if there are rational zeros, which there will be for a while here. They're going to consist of a fraction whose numerator is a factor of 18 and whose denominator is a factor of 4. So factors of 18 are 1, 2, 3, 6, 9, and 18. And the factors of 4 are 1, 2, and 4. So if you do some math, basic like combinatorics here, then you know that there's 18 times 2. There are going to be 36 possible rational zeros here, except for the redundancy. So we could probably knock a half a dozen or so out. So let's get to it. Let's be nice and organized, and let's start with the number 1. I will officially run out of colors this time. What are my first rational possible zeros? Positive and negative 1, positive and negative 1/2, and positive negative 1/4, you see. So that 1 is a busy man because he's got to interact with all of the numbers on the bottom. And that leads us then on to the second one, 2. What are his possibles? Positive and negative 2. 2 over 2, which is 1, which is already there. Positive negative 2 over 4, which is, well, half, which is already there. So actually that guy didn't have a lot of meat on the bone. So we're done with 2. Let's go on to 3. What's the first one? Next one? Good. And the next one? Good. So the nature of 3 is that he's not going to produce a lot of redundancies in this case because he's odd and the guys on the bottom are even. So you're not going to get a lot of reducing like repetitive stuff with 3. Let's head on to the 6. What does he produce? Next one. Yeah, and that's going to be it, like Bryce said. So like 6 over 2 is 3, done. 6 over 4 reduces to 3/2, done. So he doesn't produce. Again, it's that even sort of dynamic. He's going to produce a lot of repeat. Let's head on to number 9. I'll reset with my colors, go back to white. What does 9 produce? Okay, next one. Yeah, and we're seeing it again with the odd-even combo, right? That dynamic creates odd combinations. So next one. Yeah, and that's new, that's unique. So if we count these up when we're done, we'll see that I was off when I said 36, because again, there's those repeats that we omit. And then we're on to number 18. And what are his combos? And then 18 divided by 2 is, that's not 6, it's 9. And so 9 is already on there. And then 18 over 4 reduces to 9 over 2. It's already on there. So I barely almost ran out of room, but that's our full extensive list of possible rational zeros. So that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 times 2. There are 24 possibles. You're not always going to have Sutter in the back of the room who's like 3 steps ahead of us. So if we were just starting on our own, Sutter, you're not allowed to answer. What might we try? Yeah, you want to rely on Sutter, we can, just so we can get this done. I really don't care. Because I'm sure he's already found one. So you guys want to pick? Or you want, no, you don't want to. You're not into the game. All right, Sutter, what'd you get? 1. You little rascal. Good. So let's set up our synthetic division. So first lay out your coefficients. And so there are no holes here, so we can just go left to right. 4, 17, negative 39, positive 18. And turns out that 1, Sutter says, works. Let's try it out and see. By the way, I don't see any logical reason ever to start with like 9. I mean, eventually you'll come to appreciate the structured nature of just testing from left to right. But again, for today, I would encourage you to not start testing fractions yet. The fractions will pop out later. So let's do this. Here we go. Drop the 4, multiply 4, 21, multiply 21, negative 18, multiply negative 18, 0. Good. So we did find a 0, and by we, I mean Sutter found a 0. And that means now that one of our answers, I'll write it in yellow, we take this to the bank, is right here. The graph interacts with the x-axis at 1. Nice. How are we going to find the other ones? We're going to factor down what's left. So 4x squared plus 21x minus 18. So the purpose of this example was to show you that not all factoring at the end is going to be, you know, powder puff, rinky dink nonsense. This is a little harder. So this one has two possible templates. And so we're back to that. Oh man, but this is still, I think, better than muddling through testing a bunch more synthetic stuff, unless you like the synthetic better. So we'll try this a couple different ways. So we have 4x and x and 9, 2, 6, 3, 6. So yeah, so putting a 6 and a 3 like this will work. So I'm looking for that 24:3 ratio there. You see, or not ratio, but the 24 minus 3. So this works. So if I put the plus out here and the minus out here, this works. So my other answers are what? 3/4 and -6. So I just wanted to show you one more thing, and then I just have, I might give you one more example, but I think I will, because I've already eaten up the whole day. But I want to show you this, because again, this is one of those moments where you, if you're still awake and engaged and not just wanting me to shut up, you might look at this and go, that's kind of neat. So here it goes. I'm going to erase this part, and I'm going to take a different approach. Let's say you hate factoring, like factoring offended you at some points in your life, and you're like, I don't want to factor. I'm done. I hate factoring. So you could press on from here, and you can actually rebuild now and subsequently divide off of what you already got. So, and by the way, the same 0 can work again. So like you would want to try 1 again. So let's say you tried 1, -1, 2, -2, 3, -3, whatever, blah, 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 blah. And eventually you got to like 6 and -6, and you tried, because you really hate factoring at this point. Like if you're so stubborn that you're going to dig in your heels, check this out. This is neat. Drop the 4. What's -6 times 4? What's 21 plus -24? Look at that. So you can find zeros sequentially by continuing to synthetically divide if you're more into that than you are factoring. And then, of course, what happens is these two numbers right here in this white box are 4x and -3. And if you set that equal to 0, zoop, that's where you get that. Got to pause my recording. Last one. Let's call this function k. His name's k. He's a function of x. And the function is 6x to the third plus 13x squared minus 19x minus 12. So begin the process by listing out all the factors of the constant at the end and all the factors of the leading coefficient, and let's build a bunch of fractions. So what are the factors of 12? Good. And then, of course, at the front end, we've got a 6. What are his factors? So what we're going to do now is think of all those as potential fraction builders. If there are rational zeros, they will come from that list. They cannot exist anywhere else. You're not going to get like 5/8. It's just not possible. So to be nice and organized about it, we're going to make a list, and we're going to start with all of the ones over things. And so I'm going to kind of go quickly through this. We're going to have positive -1 over 1, positive -1 over 2, positive -1 over 3, positive -1 over 6. So those are 8 candidates already, and we're only 1/6 of the way done. So barring redundancies, there's 48 possible candidates. But again, we're going to be crossing some out because they've already occurred. Let's head on to the second guy, 2. What are his possibles? Positive -2, because that's 2 over 1. Positive -2 over 2 is a redundancy, so the next one is positive -2/3. Got it? Onto that, we go, we did 2 over 1, 2 over 2, 2 over 3, and then the next one would be positive -2 over 6, which is a repeat, because that's 1/3. Okay, we're on to 3, this guy right here with the little arrow pointing at him. He is positive -3. Positive -3 over 2. Positive -3 over 3, which is 1. Don't need it. Positive -3 over 6, 1/2. don't need it. Okay, so lots of repeats there. All right, we're on now to the 4. And his list is positive, negative 4. Next one. Got it. Bless you. Positive, negative 4/3 is next. And then finally, positive, negative 4/6, which reduces to 2/3. Done. On to 6. What are his? Yep, keep going. I agree. Positive, negative 6/3. That's 2. And positive, negative 6/6. That's 1. So he got a lot of repeats there. Let's head on to 12. Bless you again. And let's head on to 12. Positive, negative 12/1. What's 12/2? It's already on the list. 12/3. 4 on the list. Positive, negative 12/6 on the list. So rather than having all 48, we got a lot less than that. 24, exactly half as many. So we had like half of them were repeaters. And I'm sure that Sutter's been working on this for the last 3 minutes while we were coming up with our list. So the numbers that we're going to stack across the top to test now are 6, 13, negative 19, and negative 12, upside down division thingy. And again, I'm not going to tell you your business. Just don't choose weird things, really. Why put yourself through that? Start with the ones that you hope are good. So sure, why not? Let's do 2. We don't have a lot of time, so I'm going to try to race through this. Please don't pack up, okay? Please literally do not pack up. I will get you out of here very, very soon, I promise. Okay, so that fails. That's a 12. That's a 25. Multiply 50, you get 31. You see it fails, right? So you're going to try 1. You're going to try negative 1. You're going to try 2. You're going to try negative 2. You're going to try 3. And what would you try after 3? 4. No. Negative 3. Do not skip past until you've exhausted a number. Just because you try 3 doesn't mean 3 is dead. Another version of 3 might work like this. So drop the 6. What do you get? Negative 18, add, you get negative 5, multiply, you get 15, add, you get negative 4, and boom. And that might have been your 6th or 7th or 8th or 9th try, but you hit it, you hit gold, and then you bring down these numbers, which are 6x squared minus 5x minus 4, and you factor. Okay? Tomorrow will be a work day. I will post the assignment on Canvas, but please hold on to it or just hold off on it and do it tomorrow. Got it? Thanks, guys. I'll see you tomorrow.